Presented by Caltech.
Welcome to the Electrical Engineering Distinguished Lecture Series. As you know, today's lecture is a very special one. It will be given by an extraordinary researcher whose fearless efforts have greatly impacted academia, industry, and even our everyday lives. As someone who continues working in the fields that he pioneered, it is my great pleasure and distinct honor to introduce Professor Carver Mead. Carver is known for electron tunneling, semiconductor interface energies, the first working MOSFET, scaling of very large-scale integrated circuit or VLSI technology, structured VLSI design, the first VLSI design course, physics of computation, neuromorphic VLSI systems, and collective electrodynamics. He pioneered the silicon foundry concept and the fabless semiconductor business model. His honors and awards include National Medal of Technology, BBVA Frontiers of Knowledge Award, National Academy of Engineering Founders Award, IEEE John von Neumann Medal, Walter Wriston Public Policy Award, ACM Allen Newell Award, IEEE Centennial Medal, and Lemelson MIT Prize. He is a member of the National Academy of Science and the National Academy of Engineering. He is also fellow of IEEE, Computer History Museum, and National Academy of Inventors, among others. He holds BS, MS, and PhD degrees in electrical engineering from Caltech, as well as honorary doctorates from USC and the University of Lund. He has been a member of the Caltech faculty since 1958 and the Gordon and Betty Moore Professor of Engineering and Applied Science Emeritus since 1999. At this point, I would like you all to turn off your cell phones and join me in welcoming Carver Mead to the podium. Thank you.
Oh, great to be here with old friends and younger friends, and it's a great time. In old times, electricity was sparks since antiquity. And sparks were fun, and you could make magic with them and do all kinds of things, but there wasn't much quantitative you could do. The qualitative stuff got worked out pretty well by Franklin 130 years before our story starts. So our story is not about sparks. Our story is about controlled electrical current. And that all started when Volta came up with a voltaic cell. And here we are with what Volta patent said. If you take a copper and a zinc chunk and separate them by a blotter soaked in salt water, you get a voltage around a volt. And if you want more than that, you can stack them up. And the minute he did that, electricity went from sparks to the controlled flow of electrical current. It was huge. Faraday wouldn't have done essentially any of his remarkable findings if he didn't have voltaic cells. Here's one over here. It's just one cell. It's got salt water in it. The inner electrode's hooked to one wire, and the outer electrode's hooked to the other wire of this coil. And so there'd be a current flow, which is shown by the arrows. And he was interested in whether, when he manipulated the little coil, anything would happen in the outer one. So he hooked it to a galvanometer. Well, what's a galvanometer? Well, people had observed shortly before that if you had a current and you put it near a compass needle, it would turn the compass needle. And of course, that got turned into an instrument. Always happens. Any phenomena gets turned into an instrument. And that's a good thing. So that galvanometer then became the thing that allowed us to do electricity quantitatively. A normal compass, you have a little magnetic needle and it gets balanced on a pinpoint. So it can rotate freely, and it rotates until it points magnetic north. But if you suspend it instead of on a needle by a silk thread, then it will have a preferred place where it comes back. And so if you put a current near it, it will rotate one way or the other depending on which way the current's going. And so you'll be able to measure how much the current is. And that's the galvanometer that made all these experiments possible. Faraday used that galvanometer principle hooked up in a way that Wheatstone had figured out. He said, okay, if we have resistors set up this way, by then, of course, there was people that made resistors. Since Ohm figured out that currents got limited by resistors, then people said, well, resistors have to have a resistance. And some had more resistance, some had less. If you set them up in this situation, then the ratio of R1 to R2 is the same as R3 to Rx. Then the voltage at D would be the same as the voltage at B, and there'd be no current through the galvanometer. So by using this null principle, you didn't have to have an absolute calibration of the galvanometer, and you could still do precise measurements as long as the people who are selling you the resistors were calibrating them right. So that became the art form from then on. And Faraday used that principle to measure the resistance of lots of things. And he measured the resistance of copper wire and of iron wire, and he found out that the resistance of iron wire was a lot more than the resistance of copper wire. But both of them, when you heated up the material, the resistance got bigger. So this was a generalization. Conductors, metallic conductors, the resistance got bigger when you heated them up. Well known. Lots of theory about it. Then he started measuring the resistance of some natural minerals. And the particular one he liked because it was easy to work with was silver sulfide. And he found a remarkable thing. The resistance of the same length to area ratio, 100 times more resistance, 100 times less conductive than normal metals were. So it was kind of a conductor, but it was really only kind of a conductor. So it was a semiconductor. And that was the first time that had been observed. Well, Faraday's a very smart guy, so he kept on it. And as he heated up the silver sulfide, the resistance got less instead of more. So it's exactly the opposite of metals. That was a new deal. And so he reported that, and that became a class of materials that a lot of people studied. One of the people that studied it later was Felix Braun in Germany. And he was interested in the resistance of these minerals. There are a lot of minerals that behave that way. Copper sulfide, lead sulfide. Sulfides tended to be like that. Iron sulfide. So he was measuring the resistance more precisely. And to measure a resistance, you have to be sure that you have good contacts to the material, so that the resistance you're measuring is the resistance of the stuff and not the contact to the stuff. And in the process of trying to figure out what contacts were good and which weren't, he noticed a very interesting thing, that he could make good contacts by embedding the mineral in a big molten metal. By then there were metals that would melt about the temperature of boiling water. So it was easy to have molten metal and scrunch the mineral around in it and then let it freeze. And that made a good contact to most of them. And then he found out that if the other contact was a little wire that you put down on the surface, a very remarkable thing happened. And that is, the voltage that it took to make a given current was a lot less in one direction than the other. Or said another way, you get a lot more current in one direction for a given voltage than you do in the other direction. So this was the beginning. This is the very first electronic, solid state electronic device. A little later, a graduate student here in the US by the name of Hall was trying to understand things he was reading. It was known by then that if you have a magnetic field by a magnet like this, and you put a wire in it, that wire won't, if it's, say, a copper wire, it won't have any force on it. But if you start running current through the wire, it'll have a force on it, perpendicular to the direction of the current. And Hall said, well, if it depends on the current, it must be interacting with whatever stuff it is in there that moves to make the current. And if that's true, since the force is in a direction perpendicular to the current in a wire, it ought to be pulling on the stuff that's making the current and pushing it to the side. And if it does, let's say that the stuff that's making the current is what we call negative charges. They'll push the negative charges over to the left on this picture. And that should make the left side of this picture of the sample in the magnetic field, it should make it more negative than the other side. We take the electrical stuff and push it to the left, so it'll be less on the left side, more on the right side, or you looking at it. So he figured this out. Well, it looks just like a Wheatstone bridge. If you put the two contacts for that voltmeter on opposite sides of the sample, there ought to be a place where the galvanometer won't register anything. And he found out, sure enough, if you didn't run any current through it, it didn't register anything, but there wasn't any voltage longitudinally either. And if you didn't have a magnet to put the thing in, you could run current through it, and he could find a place along the edge where the voltmeter VH, standing for Hall, didn't register anything. So it was a null experiment. You could get a 0 point, and then you could go from there. When you turn the magnet on, he got a voltage. First time that was observed. Well, if you think about it, if the stuff that's carrying the current has a negative charge, it'll move it in one direction. And if it's positive, it'll move in the opposite way. And that means that this voltage VH will change sign depending on the stuff, the charge on the stuff that's carrying the current. So you could tell if it was positive stuff or negative stuff that was carrying the current. Remember, this is a long time before we knew anything about electrons. So electricity was just a fluid. Still a pretty good way of reasoning. He measured a bunch of things, and funny enough, some of them had positive stuff that carried the current, and some of them had negative stuff that carried the current. All of a sudden, the picture got more complicated. And that was a puzzle for a long time. Well, by then we had radio. Hertz had done his thing and had shown that you could communicate radio waves over a distance. It wasn't dependent on it just coupling by being close. And that you could steer them the way you steered light. You could make a reflector and they would go in a direction just like a reflector for a light bulb. And then Marconi came along and said, I know what to do with that. That's a way to communicate between a ship and the shore. Before that, there hadn't been a way unless you could see the ship. Well, a lot of times bad things happen to ships and you can't see them from anywhere. And it'd be really, really good to know what they were, where they were, and what had happened. So that became the first application of radio. So the ships got equipped with radio transmitters and radio receivers. How do you make a receiver? Well, they tried lots of stuff, and the original ones were really crude they took a lot of radio energy to hear anything or make any marks on tape. Marconi's first thing had a thing that made marks on tape, and it took a lot of radio power very close to go run a thing that made marks on tape. Well, and then they figured out the human ear was a lot more sensitive than that, but you had to be able to hear it. Well, what's a radio wave? Well, a radio wave is a oscillating signal at a frequency in the megahertz range, and you can hear up to maybe 20 kilohertz. So even if you could translate the radio wave into the oscillation of something like an earphone, you couldn't hear it, because it'd be pushing in one direction the same amount as it pushing on the other direction on average, and you couldn't hear anything. But if you only looked at one half of the waveform, you rectified the signal, then you could turn the radio wave on and off or change its value, and the average would pull the little diaphragm in your earphone and you could hear it. So this was an application for semiconductors, the first application for semiconductors. And in the beginning, it's like the lower picture there. They had a little wire on the end of a little knob that you could move around and try to find a sensitive spot where the wire made a good rectifier on that piece of mineral that's down in that cup. And you could poke around a little and occasionally get to hear a radio broadcast. That was a lot better than not being able to hear it, but it took a lot of fiddling around and it wasn't reliable until this guy Picard came along in 1906, and he explored contacts between different kinds of wire and different kinds of minerals. And he went through about 30,000 combinations of minerals and wires. And finally, he was able to get hold of a crystal of silicon. Actually, it was a polycrystalline mess of silicon. And he found that he could make a sharp-pointed metal contact to the silicon, and it was stable. And you could even put it on a ship that was rolling around and bumping and thumping, and it would keep working. So it was the first time there was a really reliable detector for radio waves. And the Navy got interested in that, the US Navy, and sponsored a lot of development of the use of his detector with various radio configurations. So by the time World War I came along, the US Navy was equipped with semiconductor detectors. So that was the first real market for semiconductors. Meanwhile, Bittner in Germany was interested in the physics of the semiconductor. It was known, all the people that dealt with minerals knew that every time you got a new mineral deposit, the mineral specimens would have different conductivity. And it varied all over the map. And everybody believed that that was because there were impurities in the semiconductor, and they were responsible for, it was just dirty stuff. And so it was bound to have different properties for different samples, and that's sort of the way they thought about it. And Bittner is a very careful guy, and he said, there has to be a way of figuring out what's going on with semiconductors. So perhaps I can find a way to make controlled compositions of semiconductors. And he did that for a lot of materials. Many of the materials which were like copper sulfide was a favorite of his. And that was, he could make that. And the way he made all these samples, copper sulfides and oxides were his favorites. The way he made them is he'd make samples like the shapes shown here, and the two big pads on the ends were where he put down the clamps that's shown in the side view on the top. And wow, I can make great big contacts, and then I can make narrow samples by, for example, in the B figure there, you see it's a serpentine. He could kind of scribe openings in the lines where the semiconductor had been scratched away. And so you had a path that was semiconductor that was a wandering path. So it was longer, so it was easier to measure the resistance. And he developed a whole bunch of techniques. His most favorite one was copper iodide. You see that in the bottom picture. And he made contacts out of platinum. It had really good properties. And he found a remarkable thing that with copper iodide, the way he made it, of course, is he vacuum deposited a copper layer, a thin film, which he could control the thickness by how long you evaporated the copper on the glass microscope side. And then he treated the copper film with iodine, either in a vapor or in a solution, until it was copper iodide. Beautiful, clear semiconductor film. It was a precursor to the conductors we now have on glass in all of our displays. The conductive, transparent conductors. He was the originator of all those. And he found the plot that you showed there, that as you put more iodine in the iodide film, it conducted better. So if you had a low density of iodine in the solution you treated this film with, you got a high resistance. It didn't conduct very well. But the more iodine you put in by making the concentration in the fluid that you were treating the copper in, making it have more iodine in it, or you waited longer for the iodine to go into the film, then you got lower and lower resistance. The film was able to carry current better. So it's the first time that people had a controlled way of making a semiconductor of a given conductivity. It was huge. It's a conceptual leap where you now could control the density of things that carried current by controlled chemical treatment. And that's been with us ever since. That process underlies every semiconductor device. Well, by then, there was radio. We're now, after the First World War, a lot of development had taken place. It was forbidden in the United States to even listen to radio during World War I. Most people don't know that. But afterwards, all of the people who had been doing amateur radio, of which there were a large number, were chomping at the bit because the vacuum tube had gone from a very early one in the early teens to something which was, by the 1920s, was a reliable source of radio transmission. And so it's very interesting. Irving Langmuir at General Electric really figured out how to make the modern high power transmitting tube. Because for a transmitting tube at high power, you had to have high currents and high voltages. This is one of the very earliest commercial transmitting tubes. It's called a GE Kinetron. And this was rectifying voltages up to 100,000 volts. And here's some of the other early tubes. This is the first transmitting tube that was manufactured here on the West Coast. And those vacuum tubes made broadcast radio possible because you could get enough power to cover enough area that people, a substantial number of people could listen to it. Well, if you have the ability to put something out that people will listen to, you have to make it interesting. So they started with news and entertainment, music, and it went from there. And broadcast radio then meant people wanted to listen. And here's a picture of these kids listening to their favorite radio broadcast. You can imagine what that must have been in the 20s. And it's a semiconductor detector in this little crystal set. So it's very interesting. This was the type of receiver that most people could afford. They were making receivers with tubes in them, but they were awful things. They were great big and heavy, and they used batteries. They used a big battery to light the filaments inside the tubes, and then they used another battery to make what was called the plate that would collect the electrons off the filament in the tube. And then they had to have another bias thing called a C battery. So you had 3 batteries that you had to tend, and they'd either go dead if they were ordinary dry cells, or you'd have to keep putting acid in them and checking, and it was just a giant pain to own a radio that ran on batteries. So that was the 20s, and it wasn't until late 20s when the manufacturers figured out how to make a radio that you could plug in the wall and ordinary family could afford. So in the 20s, most people could afford crystal sets, and there are 4 of them here. There are 2 homebrewed ones, and there are 2 commercial ones. And the commercial one, this little commercial one, was touted as a portable one. Now, of course, you had to have an antenna to make it work, so that wasn't very portable. But anyway, if you were close enough to a radio station, it would work with a smaller antenna. So people enjoyed carrying their radio around. This was a whole art form, and whole families or groups of kids would listen to the radio, and made possible by these big vacuum tubes, the way it went. During that period, there was a very smart guy by the name of Lilienfeld. He was a member of a group that was doing research on the brand new quantum theory. De Broglie had this crazy idea that electrons were really waves, not little hard balls, and that if you treated it that way, you got a lot of the physics that was observed. Then Schrödinger came along and wrote down some equations for that. And Heisenberg made a fancier batch of mathematics for that. And they were able to calculate the energy levels in the hydrogen atom, and it was a huge effort from 1925 on to try to understand what was going on in the world from this theoretical point of view. And Lilienfeld was an experimental guy, and he had already made some really interesting experiments that challenged the theories of the day. And in 1925, he was watching. Here was radio, and radio was going from semiconductor crystal sets, where each one of these little things, each one of these radio sets has a little cat's whisker detector, just like the one I showed you. And you can come up afterwards and look at them. Right there where you could fiddle with it because you had to. And he watched that going from this passive device, which just rectified the power that came in from the radio wave, but it didn't amplify it, didn't make it bigger. And you really wanted it bigger so you could hear it better, or you could put it on a loudspeaker. And that wasn't around there. Well, about 1906 or 7, DeForest had come up with this vacuum tube thing. Didn't work very well, and wasn't reliable. And it wasn't until 1913 that Irving Langmuir at GE came up with this kind of tube, which was reliable and could be made in volume and lasted a long time. And they made these big ones. They also made smaller ones for receivers, ordinary radios. And Lilienfeld was watching this, and it's a remarkable thing happening there. When you had amplification, you could do marvelous things. And these tube radios, although they were expensive and heavy, they gave remarkable results. And Lilienfeld said, I can do that with a semiconductor. That was a fantastic thought. And what Lilienfeld said was, okay, I'm going to take a microscope slide and I'll break it in half. That's what that little wiggly line is there in figure 1. And then I'll take a piece of gold leaf and put it in between the two halves and squeeze them back together. So now I have gold, very thin layer of gold, between the two sides of the glass. And then I can polish down the gold to where only the edge is left. And then I'll make one of my slides covered with semiconductor. In his case, he used copper sulfide. I'll make that slide and I'll cover the glass and cover over that little metal edge that comes up, which is very thin. And then I'll have a region right above the gold foil where that metal makes a contact to the semiconductor. And now I've got bronze thing, the Braun detector, a metal against a semiconductor. And what happens there is if I go in the direction where it doesn't carry much current, there's a voltage between the metal and the semiconductor. That voltage has to end up on charges. And those charges are the things that are carrying a current in the semiconductor. So I should be able to change the current carrying capability of the semiconductor by putting a voltage on the gold foil. Absolutely clear reasoning. It's the device we call the MOSFET today. It works beautifully. And in fact, each of you has one in your cell phone. It's very good for being the final amplifier in a radio transmitter, of which there's one in every cell phone, of course. Lilienfeld worked for 2 years to try to make his invention work, couldn't make it work. So he said, well, the problem is I can't really get this junction to behave like Braun's idea, where if you go in one direction, you have a voltage but not much current. I can't get that to happen. I always get more current than I should. I don't know why that is, but I could put an insulator there. I would still have an electric field between the control element which he had before as this gold foil. Now I'm going to make a whole substrate made of aluminum, and then, of course, it's easy to make a thin film of aluminum oxide on aluminum, and that was known. And then I can deposit on top of that my semiconductor film, and I'll make one spot in the middle, you can see there on the figure, which is narrow. The reason you want to make it narrow is you don't want the electrons or whatever the things are that are carrying the current to have to go very far, because it would take too long. So if you want something that works fast, you have to have the path that the current goes through be short. And of course, we've played that game for a long time now. So this is the device which also dominates the modern world. It's called the MOSFET. That stood for metal oxide semiconductor field effect transistor. And the field effect means there's an electric field that changes how many current carrying charges there are in the semiconductor. This is by far the dominant type of device you have in your cell phones, your computers today. So both of Lilienfeld's inventions are not only workable, but they're extremely important, this one being by far the most numerous. Well, meanwhile, his colleagues, more theoretically inclined, were trying to figure out what's going on in solids. What makes a metal conductive? What makes an insulator, and what makes these crazy things in between be in between? They had this idea, you could just take Schrodinger's equation, which treats the electron as a wave, and if it were out in a vacuum, it would be a nice parabola. So if you just looked at the left-hand figure and you just sort of smeared out those dark curves, it would be a nice parabola. That's the energy of a propagating electron going as the square of the momentum. Well, even classically, an electron has a kinetic energy of, the momentum squared over the mass. So it should be a parabola. But if it's a wave and you put it in a crystal, well, the crystal has positive charges. If you're going along, it isn't just out in a vacuum, it has positive charges. So there will be an interference between the wave of the electron and this periodic structure. So it'll act like a diffraction grating for electrons. And what does that do? Well, they found that it would create gaps in the energy that an electron could have and still propagate in the crystal. And so if they blew up the left-hand curve and look at it in the right-hand pictures there, the very bottom of the curve had an energy which is going like the square of the propagation constant, which de Broglie had said was the momentum. Okay, that's right. But then it got to the point where it's funny. Instead of being curving upward, it would be curving downward. Then I got to a place where there weren't any propagating solutions. And then you go up in energy a while long, and then it starts another propagating solution. And the curvature of these waves is like 1 over the mass in the equation for propagation. Well, so that was interesting, because if you had an electron at the top, like there, that electron is in a region where the energy is slowing down the propagation instead of continuing to increase it. Well, that corresponds to something different. And if you just think about the mass of these things being 1 over the curvature, then down at the bottom, the mass of those little electrons shown by those little hash marks is positive because the curvature is positive. Well, when you get up to the top one there, the curvature is the other way, so that's something that has a negative mass, which means that if you push on it, it'll accelerate in the other direction. That was the answer to why do some of these things that are carrying current look like they're positive things. They're called holes, and about half of the devices that you have in your cell phone work with those as the carriers of current, and the other half work with ordinary electrons. And then World War II started, and everybody went to war. And in the US, they didn't get into the war until 1941, but you could see it coming. So there was a lab set up in MIT called the Rad Lab. That building there, they just took over the whole building, and they built a little hutch on the top, which you can see. And on the upper right-hand picture, you can see people working on electronics and antennas. That was in that little building on the top there. And the lower right picture shows a glass blowing shop they had so they could make their own vacuum tubes, and they could make the little packages for semiconductor devices and do all that stuff. And they also contracted with industrial firms, in particular Bell Labs and General Electric, and they contracted with a bunch of materials labs that worked on getting better materials. And guess what materials they picked? Well, Picard had shown that the only reliable point contact detector you could make was silicon. Well, why did they need a semiconductor detector? They had vacuum tubes. Well, you were going to put these radar sets in airplanes, and they could only be that big. And to get a beam, it's just like optics. To get a narrow beam, you had to have a big enough mirror, and that had to be many wavelengths across. So for that, that's only a fraction of a meter. You needed waves that were like a centimeter wavelength. That's 30 gigahertz in today's nomenclature. There were no vacuum tubes that come close to that. The very highest frequency vacuum tubes at that time would go to a gigahertz. So you had to go to higher frequencies, and that meant you had to have something which was very small, and the only thing they had that was very small was bronze detector. So here's bronze detector on the right. And what did they make? They made Picard's detector because it was the only thing that can be made reliably. And the lower picture there shows how it was built. It was built with a little piece of silicon, you can see it's labeled there, and a cat's whisker. But just what Braun had done, just what Picard had done. Just make it, and make it reliable and fly it. And that's what they did. So the upper left there is the current voltage curve for that device that was made in the Rad Lab. And the right-hand one shows Braun's device. They're the same thing. A cat's whisker on a semiconductor. It just turned out that silicon was the most reliable according to Picard. So they worked harder on it. And they also worked on its its twin in column 4, germanium, because some people thought that would work better. And both things were developed, and there was a lot of materials work done to make the whole thing work. And it worked. And they flew the radars. Halfway through the war, a German scientist, Schottky, he was a dogged fellow. He had been trying to understand the metal semiconductor contact ever since Braun had shown it. And he kept coming up with theories, and they kept being wrong and being shown to be wrong by experiments, many of which Braun had done. And by 1942, it turns out that the German publication Zeitschrift für Physik was still being published, even though the war was raging. And Schottky published this paper which said, okay, I know how this works. He took selenium, which was a semiconductor, and found that the impurities that were in selenium were atoms that had an extra positive charge that could come off. We'd say today they made a p-type semiconductor. And so if you put a metal up against it, there would be some relationship between the energy of electrons in the metal and the energy of these positive things over in the semiconductor. And if I put a positive voltage on the metal, that was a direction that not much current would flow because there's an energy barrier there. And that's this phi plus thing. And so what would happen? Well, there's a positive voltage on the metal. I have to have a negative charge on the semiconductor to absorb the electric field lines that come from the positive metal. So what would that be? Well, if I push the positive charges that are the mobile things that'll move, if I push those back, then what's left is the atoms where those positive charges came from, and they have a net negative charge left over because they were neutral atoms when they came into the crystal. And so the region that had the electric field in it would expand as I made a larger positive voltage on the metal. And indeed, he could measure the capacitance, which is like 1 over the thickness, and went just exactly the thing you would guess. The voltage is the electric field times the distance. The electric field is the amount of charge, which goes like the distance, so the capacitance should go like 1 over the voltage squared. And if you plot it, it did that. So that was the first theoretical understanding of what went on in these metal semiconductor contacts. And that turned out to be a key thing. One of the labs that was contracted by the Rad Lab to do work on these point contact, Braun style, Picard style detectors for radar was Bell Laboratories. And they quite properly saw that here someplace there's a semiconductor device that will amplify. So Bardeen, who's a left-hand figure in this publicity picture, said, hey, when we have a reverse biased point contact, there'll be a region around it which you push the carriers out of, just like Schottky said. And if you put another little contact up there, you should be able to measure the extent of that region. So Bratton, who's the right-hand figure on this slide, was a good experimentalist, and he made a thing with two little manipulators that you could make 2-point contacts and get them real close. And as they were measuring what happened, the metal contact on the left, they noticed it affected the current in the metal contact on the right. Well, that's interesting. The current that you put into the metal on the left, a fair fraction of it came out of the metal on the right. You'd say, well, there's no gain in that. You've actually lost some of the charge. Yes, but the metal on the right is a reverse bias junction. It's the one where if you change the voltage, the current doesn't change much. So that's a high impedance device. And on the left, that's a forward bias device. If you change the voltage a little, it changes the current a lot. So if the two currents are anywhere near, you get a gain that's like the ratio of the impedances. So to test that theory out, you went to the bottom right diagram there. You just make a transformer. And you use a few turns on the left-hand one and a lot of turns on the right-hand one. And so you tune them both to the same frequency. And it oscillated like a banshee. And that was the first understood active device. It turned out there had been devices that would oscillate. These Picard-style devices, Picard had found some that would oscillate. And there was a Russian by the name of Lossev that had gotten a little better at making things that would oscillate, but they were never really understood or controllable. But this was the first time that there was a thing that it looked like you could control. Well, Bardeen, being a fantastic intellect, said, I'm going to understand this thing. How could a metal contact work to put things that would carry current that were of the opposite sign that you would expect from that picture of Schottky's? And it turned out that he figured out how it was. There was this energy barrier for the current carriers that were there in the semiconductor. They would go over the barrier to the left from the right-hand side of the picture. But also, there were the other sign of carrier, which above the Fermi leveler, that would go to the right over the barrier and become opposite sign carriers in the valence band. And that was what was being observed. It was not the current that was coming the way you would expect and the way it worked for all the other things. It was coming the opposite way. And that was a property of germanium. And that was why the first transistor was discovered in germanium. Well, Shockley was not to be left out of this party. He was not at all shy about getting into the party. And he actually was the one that figured out really what was going on. If Bardeen's theory was right, then what it really was like was you had one kind of semiconductor that had one kind of carrier. Let's say an N-type, had electrons. And then you had the other one on the right-hand side that was N-type. And then in the middle, you put up a little sliver of P-type. So if you forward bias the junction between the N and the P on the left side, and reversed biased the N-P junction on the right-hand side, then you had a thing that worked just like that point contact transistor did, except you could make this reliably. You'd have to worry about that little. And that was the birth of the transistor as we know it. So Shockley actually deserves his position there in the center of the photograph. This was the photograph from the publicity photograph for the Nobel Prize that was given to the three of them. Well then, how do you actually make these things? Well, there are a bunch of things tried. And early transistors were kludges of various sorts. And finally, this guy Penkov, whose real name you couldn't pronounce, so he changed it, invented this incredibly simple and reliable way of making transistors. You took a piece of germanium and you put a little pellet of indium on both sides, and you put it in an oven until the indium melted. And the indium dissolved a little bit of the germanium. And it was very controllable because the solubility of germanium and indium goes up very slowly with temperature. So you could get a temperature where it went in just a nice controlled amount. And then you cooled it down. And the germanium that had dissolved in the indium crystallized back out on the germanium that was there. Well, the germanium that was there was N-type, and indium is a P-type dopant. It takes an electron away, and what's left is a hole in the valence band. This was a PNP transistor, P from the indium on the left, P from the indium on the right, and N-type because that's what you started with. Incredibly easy to manufacture these things. They would only operate up to about a megahertz, but they were a transistor. Raytheon brought out one called the CK722, and that was the only thing you could afford to do in lab. And so a lot of us grew up making these very low frequency circuits out of this kludgy transistor, but they were only $1, which was a lot more in the 50s than it is now. Well, then it was clear that this was a route to manufacturability. And Philco, who was big in electronics in those days, came up with a fantastic technique for making transistors. They were going to tool up to have an automated factory, which I was able to tour in the either late 50s or early 60s. And what they did is they had a little flake of germanium, and they had a little spout on both sides, and they would squirt electrolyte on the germanium. And if you put a current into the electrolyte in one direction, it would etch away the germanium, and if you put the current in the opposite direction, it would deposit indium. So this was an automated way to make these PNP transistors. And well, how do you know when to stop? Well, it turned out that germanium absorbs infrared light, and of course the amount you absorb goes exponentially with the thickness. So you shined light, this made a little light pipe, this electrolyte. You shined infrared light down one and looked at how much came out on the other side. It was very easy then to know when you get this much light, you reverse the polarity and you deposit the indium. And then they had this factory running. The thing would get indexed over to the next thing, and the wires would be put on, and the whole thing came out as a packaged transistor. Ka-chung, ka-chung, ka-chung. And I got to tour that factory in Blue Bell, Pennsylvania. Very impressive. So here was an automated way to make economically feasible transistors. And also, you could reliably make the region in the middle, the base region, very thin this way. And it made good transistors. And instead of a megahertz like the CK722, these transistors would oscillate at 70 megahertz. That means you can make radio out of them. So they thought they really had it made. But meanwhile, some Bell Labs guys were working away on silicon. And they said, I can put impurity atoms in silicon by diffusing them. And if I want to make a junction, I just diffuse in the, and it was known how to diffuse impurities into silicon, but I only want to diffuse them in a very narrow area. Well, I just oxidize the silicon silicon oxide, one of the best insulators in the world. And then I use a photolithographic process, which are well known from the printing industry. And I cut a hole in it with hydrofluoric acid. You can dissolve silicon oxide with hydrofluoric acid and it won't attack the silicon underneath, so it stops at the right place. And then I apply some of the impurity atoms and I heat them up and they go diffuse in, and I've just made myself a junction right where I want it. And I didn't have to have jets of stuff and deposit things hanging out in the air. This was just on a surface of silicon. And if you diffuse things in right, you could diffuse one kind of dopant in a short distance and then diffuse another kind in a longer distance. And if you had started with the right dopant, in this case, you started with a low concentration of N-type material, and then you diffused N-type material in, but you diffused in a P-type material that diffused faster. So what you got was the bottom left picture there. The net doping, the net concentration of impurities was N-type near the surface, N-type far in, and P-type in the middle. That was an NPN transistor. Well, electrons in silicon go faster than holes do. So this was a fast transistor, and they showed because you can really control the depth of the junctions by this diffusion process, which is just a chemical process. You raise the temperature a certain amount and the diffusion happens at a certain rate, extraordinarily well controllable, down to fractions of a micron. So you could make a transistor that had submicron dimensions vertically by this diffusion technique. And all of a sudden, the transistors, instead of being 70 megahertz, were 400 megahertz. And silicon had bypassed germanium as the speed record. And you could make a whole bunch of these transistors on a single wafer of silicon. So that's when it dawned on people that we weren't going to make economical transistors by a machine that went ka-chunk, 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 and it would do etching and it would do depositions and stuff. We were going to make economical transistors by making lots of them on a single piece of silicon. That was a huge, huge. Then started the migration of expertise from the East Coast centers to the West Coast. This was the first one, Pacific Semiconductors, Inc., just right down here in Culver City. And they quite properly saw that there had been a big furor over transistors because the vacuum tube people said, yeah, you can make these little transistors and they'll be good for hearing aids, and then as they got faster, well, they'll be good for little transistor radios. But we're going to be making the things that make transmitters work. Our vacuum tubes, we can miniaturize those and we can make them work at higher frequencies and we can beat you guys. And there was a period where there was a lot of pulling and hauling over, could you make military specification transistors that would compete with vacuum tubes? And the jury was out on that. But the issue came down to, you can make these little transistors and they can work at high frequencies, but that's because they're small. And the people at Pacific Semiconductors saw that you can make a big transistor by making a bunch of little ones in parallel. So they started doing that very early on. And by 1956, they had transistors like this on the market that would dissipate 50 watts. They'd run it as good amplifiers at 120 megahertz. You could make radio transmitters with that. And so that settled the argument. You don't need vacuum tubes to make all the technology. And as this art form evolved, that's what happened. Well, the biggest single step in this evolution process toward the technology we have today was this one. Bill Shockley had come to Caltech for a year and he met Arnold Beckman. And he convinced Arnold Beckman to bankroll him to start a little research lab up in Palo Alto. And he did that, and he went around and handpicked a bunch of very bright young PhDs. And within months, they had record-breaking transistors that they were making. And everybody was excited. And Bill said, no, transistor, that's all known. We're here to do something new. And he quite properly saw that if you made a 4-layer device instead of a 3-layer device, you could make something that would switch power really well. And that's the kind of thing that's in all the light dimmers today. So he was right. But what he didn't see was switching power wasn't going to be the explosive market. It was representing information electronically that was going to be the explosive market. He couldn't see that. These guys did see it. So they got together and they said, we're out of here. They went back and met Sherman Fairchild, got him to bankroll this little company that, of course, was called Fairchild because he put up the money. And here we are. There's Gordon Moore. There's Jean Herney. And there's Bob Noyce. And those are the people who made the key steps in our modern technology. Well, meanwhile, technology was evolving everywhere, and Texas Instruments was not to be left behind. And they were the first ones to introduce a good high-frequency silicon transistor. And Jack Kilby looked at this and he said, you're making transistors on a wafer. I could connect them up and make a circuit, because if I have a diffusion in a wafer, I can make a resistor out of that. And if I have 3 diffusions vertically, I can make a transistor out of that, and I can hook them up, and that would be a transistor all on the same wafer. And that was right, but what Jack didn't have was a way of hooking them up. So he had these flying leads that you can see on this picture. You could bond them up with bonding wires. Well, that's not an integrated circuit. That's a circuit that's all made on one piece of silicon, but it had to be hooked up by individual external wires. So he had a good vision, but no way to get there. What he didn't know was, at that very moment, Jean Herney had invented this thing we call the planar process. And what it was you started from one side of the silicon and you diffused in the first layer, and meanwhile, while you diffused it in, you let an oxide grow on the surface. That was the insulator. Then you could cut another hole in that oxide and diffuse in another region, and now you had a transistor. And then you could cut holes in the oxides where you wanted them, and you'd hook up any one of the elements of the transistor, and they were all separate. And in Jean Herney's patent, figure 10 down at the bottom, you can see you could get a wire to any part of the transistor, to the emitter, to the base, and to the collector. And that wire could be the aluminum that you use to make a contact. And of course, Bob Noyce signed Jean Herney's patent disclosure. And he looked at that and he said, Jean, we can make a real integrated circuit with this. So Bob filed that patent. And so the Herney and Noyce insights were what gave us our modern integrated circuit. And Jack had a really good idea but couldn't make it. Well, there have been some important inventions since then. I have to mention this one because John Atala at Bell Labs worked for many, many years to try to figure out that silicon-silicon oxide interface. It's a complicated thing. And everybody who's tried to make silicon devices runs into all of the things that can happen there that'll kill you. But these guys at Bell finally kept at it until they were able to make really reliable silicon oxide interfaces. And that made possible Lilienfeld's second invention, the MOS transistor. Here you had a metal on top, the oxide on the silicon, and then the silicon was your semiconductor. So that was the first real commercial field effect device. And as you can see, it's a very simple device. You don't have to have so many layers vertically. One more thing that was important, if you're going to make logic out of a circuit, that means you're going to represent a 1 with some voltage and a 0 with a different voltage. And that means that you have to have a transistor to pull the output up to the voltage that represents a 1, and you have to have a different transistor to pull it down to a voltage which represents a 0. Well, Frank Wanless, also at Fairchild, quite properly saw that if you did things right, you could hook up like figure 5 there, which had a top transistor, which is a p-channel device. So if you made the gate low, it turned it on, and that pulled the output up. And if you made the bottom transistor an n-channel device, you could hook the same input to it, and when that input went up, it would pull the output down. But when the output was steady, both devices were off. Let me say that again properly. When the voltage on the input was steady, one device would be off and the other one would be on. So the output would be held either at the bottom potential or at the top potential, but there wouldn't be any current flowing because always one device would be off. And by hooking devices in series and in parallel, you could do logic. That's what figure 8 and figure 7 are about. And then the big one on figure 8, you could do it on an integrated circuit. And he spelled out the way you would make that integrated circuit. So that's the modern CMOS, and that's what's in all your computers, and that's what's in your cell phones. And of course, I have to mention a couple of other things. Bob Denard at IBM came up with a manufacturable way of storing charge temporarily on a transistor gate and then coming back and reading it, and in the process of reading it, refreshed it so that even though it was decaying away, you didn't have to have something pulling it up and something pulling it down, because that took it took at least 2 transistors. But this way, you only had to have 1 transistor, and you just came back once in a while and refreshed the charge that was there. And that's the dynamic RAM, which is the workhorse memory in your computers. And I can't resist. There was one more thing that Lilienfeld did, and that was his very first thing 40 years before. He had come up with this MOSFET device, and nobody had ever been able to make one. So this one was made right here at Caltech, and that's how I got to know about Lilienfeld. And actually it it made me feel really good that I could finally make something that Lilienfeld had completely, clearly invented, but was never able to make. I just wish he could have lived to see it. Well, from then on, Gordon Moore, 1965, he made this plot. He gave me this copy. He also gave me one of the original ones, but I couldn't find it. The original ones are in the black. And Gordon said, you know, we're getting more and more transistors on the same chip every year. It turned out that what had been a quest for new and better electron devices became a quest for how do you do the ones we know work that are smaller and faster and dissipate less power. And just put your head down and do it. And the people that did that beat out all the people who are trying to be fancy. And what's happened is Moore's law, and this is log to the base 2, so it started at 64 devices on a chip. We thought that was pretty neat. Now we have billions, and it's still going, but a lot slower. So you always wonder, looking back, does it teach us something? Well, there are really 3 threads in this period, and I've only really talked about one of them with just occasional references, but you know, you'd think, looking at the history, that this vacuum tube stuff was a giant diversion from the straightforward evolution of, you all have this in your handout, so well, but that wasn't true, because there wouldn't have been a market for semiconductor devices if there hadn't been radio, and there was nothing that was going to make a reasonable radio broadcast technology except the vacuum tubes at the time. So they made the market for semiconductor devices. And without that market, they wouldn't have been developed. So it's kind of odd. People often ask me, what's next? We're on Moore's law and it's slowing down. Steve here is a big proponent of doing the same thing better and faster with the next generation. And he's made a lot of these field programmable devices that are leading edge use of silicon. And even Steve is getting a little queasy about, well, Moore's law is not going so fast as it used to. Is there going to be a next generation of stuff, and what's it going to be? Well, you don't know about these things. I can tell you from personal experience that here we are working hard to make new and better electron devices. And then Bob Noyce comes up with a way of hooking them together. I never thought about that. It's a good idea. Then Gordon comes along and says, you don't need new and better kinds of devices. Just make them smaller and keep going. And you know, Steve probably did that more effectively than anyone I know. Didn't think of either of those things at the time. Well, there's something that's just happened in the last 10 years, and that is the way devices are used was really structures that we knew about, things that would multiply, things that would add, things that would store, and things that would, sequence. And you can make computers that way, you can make memories that way, you can do all that stuff. And then here comes this new thing, which we're all working on 30 years ago, that we called neural networks back then. And it turns out that now the technology, for some reason, will do those really well. And so people are all making different interactions, different structures on their silicon than they did. And Steve's thing's actually still in the running for that, and that's a good thing. That was not an expected thing. When we were working on it, we thought that would happen, and nobody would give us the time of day. That was 30 years ago. And now everybody's all nuts about it. The principle hasn't changed at all. It's just that we got enough stuff and it runs fast enough that now it's feasible to do that in a commercially effective way. I wouldn't have expected that. I expected it 30 years ago. I gave up. So we don't know at least I don't know what's coming next. There are lots of ideas. Maybe it's vacuum tubes. You know, you notice here in the middle column, down by the bottom, Ken Shoulders in the 60s was making vacuum tubes that were a micron in size. They worked really well. And he figured he could make integrated circuits out of that at about the same time that Fairchild was off making integrated circuits. Never went anywhere. Well, right now, our very own Axel Scherer is making little tiny vacuum tubes. And now they're nanoscale, not microscale. And the kind of physics that goes with devices that size scales really well. And electrons go really well through vacuum. It's a good medium. Maybe vacuum tubes will come out. Who knows? I'm not going to poo-poo anything. But it's going to be very interesting in the next 50 years. It's been 50 years since Moore's Law. And one of the things that's happened is all the people that were good at figuring out how the devices work and inventing new ones and stuff, they're all retired. They're not. And that lore has not been passed on to the educational system. So right now, we don't have a group of people who are good at inventing the next technology. But there are a few out there, and I wouldn't count them out. So let's watch and let's root for the next generation. You're welcome to come up and look at the exhibits afterward.
Oh boy, I went way off.
Carver has offered to answer a couple of questions. So, but please wait for us to give you the microphone because this is being recorded. So questions?
So thank you very much, Carver. That was a wonderful, as always, talk. What was the biggest kind of like mistake that people made in your mind in terms of the way they did things that didn't pan out? What was the things that they shouldn't have done? I mean, in retrospect, these things are easier to see.
The biggest disappointment for me was that Lilienfeld didn't discover selenium. It's such a tragedy that he didn't get to see his devices back when he knew they would work and he was working on them and he was an incredibly talented experimentalist. And neither one of them would work with the stuff he chose. So he stuck with copper sulfide. If he'd have just gone to selenium, he'd have had it. And then we'd have had a whole different evolution curve. Would vacuum tubes have been obsolete? I think not. I think we still would have had a race between the vacuum tube and the transistor, but it wouldn't have taken so long. That to me is the ultimate tragedy in this story.
Any other questions?
Oh, here's one over here.
What do you think about bottom-up assembling of devices, autonomous self-assembly of devices? Do you think it's a future, molecular devices? And so you don't need to have like a huge,
good
expensive
question.
facility.
What about self-assembling devices? That might be the next thing. My guess is it's going to be a little like our, what's now called deep learning, that it'll take a while for it to become, but there may be an application area where it just fits and you get an early start on it. That's certainly one I'd be watching. Oh, I should say something about that. If you're going to have a self-assembling technology, it's not going to be 100% reliable. So the application is going to have to be fault tolerant. And people are getting better at that, but not on the scale that I think is going to be required for that to become commercially viable. And neural systems are the only things we know that tolerate massive kinds of errors and learn around them. And it could be that there's some kind of interface between those two things.
Carver? How would you recommend that we go about, in particular Caltech, go about creating the generation of the creative people needed to figure out what these next things are going to be?
Well, one of the advantages we have here at Caltech is that there are a lot of very unorthodox directions being explored. And you don't expect all of them to be a home run at once, but we get more than our share. And I think as long as we don't get a big group thing going, where everybody's pulling the same direction, there'll be enough creative things that are being explored that we'll have our share of the ones that push things forward. What you don't want to do is just get a big group think where everybody has to be marching to the same drummer. And Caltech is better at that than most places.
Carver? I know you've been heavily involved both in research here in Caltech, industry, so you're in a good position to answer. I always wondered, transistor was invented at Bell Labs, but the AT&T system, Western Electric, AT&T, which was the mother company of Bell Labs, was one of the last companies to actually benefit from the transistor and adopt it for its own natural system. What is the economics, politics that the transistor was put into action by maybe TI, Hitachi, but not AT&T, not the Bell system? Why?
Well, of course, I wasn't at the Bell system, but I can tell you that by the time we were doing this stuff, the Bell system was heavily interested in being the big dog in the applied science area. And that didn't help in terms of creativity. But also there was the consent decree that they were not allowed to benefit immediately from their inventions. So that kind of put a damper on the commercialization. And they were forced to license everybody on reasonable terms, which they did and did very well. So that put a damper on it. But as late as The MOS transistor, they were leading edge in terms of the research that was going on at Bell. So it's complicated. I don't, I couldn't give you a one-liner.
In your beautiful recount of the history so far, it seems that even though it went through the two world wars, it was mostly just put aside as a distraction to the technology development. But nowadays, technology has a very strong political side, and I wonder how you think about politics and what's going on outside of technology will influence how technology would go ahead in these years or in the future.
Well, it's certainly true that technology today has a huge groupthink going. So, and it's a natural result of the fact that that's what's been rewarded. It's just doing the same thing better. And so any new thing has to be much, much better, not just better, in order to get to break through any groupthink that's just doing what we know how to do. I think Caltech's in a better position to do that than other places. It's still not easy because you're going against the flow. And every one of these inventions, these are incredibly clever people that understood perfectly well what was going on. After, a lot of this transistor stuff had settled, and we had bipolar transistors, the NPNs and the PNPs, before the field effect devices had taken over. There was an analysis that appeared in one of the magazines about Lilienfeld's invention. And the guy that analyzed it thought it was a minority carrier device, because he could only think one way. Now we had minority carrier devices, so that was what it must have been. So the groupthink thing is extremely strong. And so if you're going to go past it or against it, it's not going to be easy. I think we're getting late.
Yes. So maybe we stop here. There is a reception outside that you can hang out and network, and they can take a look at.
Yeah, look at that, and I'll be here if you have.
If you're not too tired, you can maybe answer some more questions over there.
Yeah, we can do that while everybody's getting something to eat. Yeah.
Thank you.